Swayam Prabha. Digital India. Educated India.
In the last lecture we had started looking at the components of system design, and we had started with the application rates. We had said that the application rate is of two types. One is gross application rate and the other is the net application rate, because these two are, they can be very different depending on the conditions prevailing in the area. Let's look at the various expressions which we use to get the gross application rates and the net application rates. The gross application rate if we express this as dg as a function of the sprinkler nozzle discharge and the spacing of the sprinkler heads. In this expression, the dg is the gross application rate and is given in centimeters per hour. This Q is the sprinkler nozzle discharge, and this is given in liters per second. And these we have already seen that these are the spacings. This is the lateral spacing and the main line spacing. Both are in meters. As per our discussion in the last class, we had mentioned that the gross application depth or the gross application rate will be affected because of the losses, which are mainly because of the evaporation and wind drift losses. So accordingly, the net application rate let's call it dA will be the gross application rate into 1 minus LS, where LS is the evaporation and wind drift losses and traction, and dG is the gross application rate in centimeters per hour. So dA will be also in centimeters per hour. This quantity will be very important to be assessed, because ultimately whatsoever you want to apply to the ground, that is more important. The net irrigation rate is more important than what is coming out of the nozzle. As the nozzle discharge is, if it is, most of it is going to be lost, then I think is not going to give you the end result, which is the yield of the crop, because the yield of the crop will be dependent on how much of that has been absorbed by the soil, and which is basically dependent on the net application rate. So the net application rate in this particular case is, since the variation can be large in terms of the evaporation and the wind drift losses, so the net application rate, a proper evaluation of the net application rate takes much more significance than you will find the loss rates in the other irrigation systems, where the variation is not that drastic as in comparison to what you can get here. But at the same time, you might land up with a situation where you have found that there are some losses which are known, which you can evaluate, and after taking into consideration those losses, you find that the gross which becomes available, or let me put it the other way around, that if you know a gross and out of that gross the losses are very significant, the remaining portion which is left is the net irrigation rate which is applicable. If that becomes very small, in some cases it might happen that is not applicable, is not you might not be able to apply that rate. So in that situation you will have to come out with some rates which are implementable, so that after taking care of the losses there is some net which can be implemented onto the field. So from that angle, there has to be some lower constraint which has to be put on the gross application rate, which is what has been recommended after a lot of experimentation. And this particular chart, or this table, which is giving the recommended minimum gross rate, is dG in centimeters per hour for different climatic zones, and the values of these gross application rates, the variation which has been given, that in case your gross application rate is working out to be lower than this, it might not become practicable. You might have to adopt the rates which are these recommended rates, otherwise your efficiencies will be really very drastically affected. So for a cool maritime climatic zone, your gross application rate can vary between 0.25 to 0.4 centimeters per hour. For warm conditions, the warm maritime conditions, the rate is 0.4 to 0.5. For cool dry continental conditions, is again the rate is 0.4 to 0.5 centimeters per hour. Similarly, for the other conditions, these are the recommended rates. So you can see here that the variation is really very large. As the climatic conditions change, your minimum gross application rate, which can be effectively applied, that really varies drastically from 0.25 to somewhere around 1.9 centimeters per hour under the worst conditions of hot desert conditions. This is a very important aspect, that you must check these recommendations are basically made available to check your design parameters under the prevailing conditions, whether those conditions will be achievable or not, because when you are making calculations, there you won't get the feel whether these things are really, these parameters are the parameters which can be implemented. So for that purpose, all these recommended values have been obtained after a lot of experimentation all over the place, and these are the ones which are recommended in literature so that the designers can take help of these findings. Now similarly, there are guidelines on the maximum net application rate which can be implemented at a particular site. And when you talk of the maximum application rates, the criteria, the major criteria is that you shouldn't have a rate which can produce runoff. So that being the governing criteria, there shouldn't be a rate which should, you should provide the application or the rate of application in such a manner that under the prevailing conditions, your runoff generation should be avoided, which means the slope will become a very important aspect. If you are looking at the minimum, the maximum application rate which can be applied, which is the net application rate, you have to consider basically the soil characteristics, which will decide what is the infiltration rates, and the slope, which will decide what will be the velocities which can be obtained, and even the infiltration rates can also be affected because of the slopes. So the recommended values which have been given for the maximum net application rate which can be used under different conditions of soil texture and profile and the slope. These are divided into these broad categories: the coarse sandy soil, that is the soil texture, and the profile is given in terms of whether the depth of the soil is less than 2 meters or beyond 2 meters. So if is the to 2 meters of soil, and the other condition is the coarse sandy soil over compact soil. In this case, the profile of the soil, this is the shallow soil, this is the deep soil. So if you have deep soil, then you can afford to have a higher level of net application rate. The maximum net application rate in that situation can be 5 centimeters per hour for a slope which is very small slope, 0 to 5%. As the slope increases, you will find that the maximum allowable net application rate will reduce, and the reduction is quite significant. Now these limiting values, they are obtained with respect to the situation that the objective that there shouldn't be any runoff produced under these conditions of soil texture, the soil profile and the slope. When you have more compact soil, the profile is less than 2 meters, then you have these recommended maximum net application rates which should be utilized. Similarly, in the other cases also, to 2 meters and over compact soil, you have these recommended values. And in the case of silt loam, you can also observe that as you go from the coarser soil to more heavy soils, your rate of applications are also reducing, and the reduction is also quite significant. And this, for example, from 5 centimeters per hour, it has come down to 0.8 centimeters per hour for silt loam under the compact conditions. In the case of heavy textured clay or clay loams, the profile of the soil doesn't make much of a difference. So there is only a single case because it is not very much affected by the profile. The soil texture itself is the more influencing factor, and as such the rate of application is very small. So in the case of heavy textured clay or clay loams, you will find that there is as such the rate of application which is allowed or which is permissible if you want to avoid the surface runoff is a very small rate, varying from 0.4 centimeters per hour to 0.2 centimeters per hour. Then besides the application rates, the next item which is quite important is the sprinkler nozzle discharge. The sprinkler nozzle discharge, it varies with respect to the pressure, which is the prevailing pressure, and it can be expressed with this function, where Q is the nozzle discharge in liters per second, and P is the nozzle operating pressure, and kilopascal, and K is the proportionality constant which depends on the diameter of the nozzle and the model of the nozzle. What is how the nozzle and how the nozzle is manufactured, what type of nozzle they are. It will be a function of the model of the nozzle as well to a certain extent. So the K values are normally not given directly. They are invariably available in terms of the tables, which are rating tables given by the manufacturers. When a manufacturer comes out with a new model of the nozzle, they will give you a accompanying table which will have all these different items which you are interested in from point of view of the discharge calculations or for other parameters which are design parameters. Those things are normally made available, and a typical table which will be made available for a specific nozzle. There is one table which we have taken, which is the table provided by the manufacturer for a specific model of the nozzle which has a diameter of 3.175 millimeters, and the other the discharge variation is given with respect to the pressure variation and what will be the wetted diameter. So these three things are related. For a specific diameter of the sprinkler head or the sprinkler nozzle, you will find that with the variation of the pressure, your flow rate or the discharge rate will also vary, and the diameter, the wetted diameter will also vary. This might give you the total pressure variation, but along with that, there might be a minimum recommended pressure. For example, in this particular case, it might be given along with that you should use this range of pressures on this level, give you the minimum recommended pressure. So below this are the pressures which are recommended pressures. You can choose with respect to what is the prevailing pressure available, how much can be obtained under the conditions, and accordingly what is the flow rate which will be obtained if you run the sprinkler under this pressure, and this will be the wetted diameter. Now these wetted diameters are again, they are the diameters which are without the wind conditions. If you will have the wind conditions, then there will be some change in the wetted diameter. Those things can be incorporated if you know the wind conditions, what are the prevailing wind conditions. Let's now go on to another item, which is the sprinkler spacing. All these items which we are discussing, is very important to understand that these items are the items which you will have to check your design for. In some cases, you might be having available, or some of these items might be fixed. For example, when we say that we want to select a particular nozzle. Now if you are going to select a particular nozzle, then you might have a choice. In many situations, you might be already having some nozzles which you want to make use of. So if that is the situation, in that case, your constraint, the design constraint becomes that you want to utilize a particular nozzle, which might be a generic nozzle, size which you have procured and kept with you. Because as a farmer, you try to visualize that when you are going in for these systems, you might use the sprinkler system for different types of crops. And if you have a very big farm, your conditions, the soil conditions also can vary in certain cases, or if you have farms at two different locations, the soil conditions can also vary to a certain extent. But let's take that, keep that out for the time being. Let's talk of a specific farm. Now, when you vary the type of crop which you might be using from one season to another season, in that case, you might find that if you go in for a fresh design, you might find that you might need a different sets of the equipment. The equipment can be in terms of the nozzles, the size of them, and different size of nozzles, or the laterals, the main pipes, all those things. In many situations, you will like to fix these items if they are already available, or you might procure those items which are in between items. For example, if you can use a sprinkler nozzle which is one level of size, and you might take another level which is the next level, so that the variation is not much. You might use those intermittently for a slight, for taking care of a slight variation in the requirements or the application rates. So all these items we are discussing separately. Ultimately, you will have to have a trade-off between these things with respect to your constraints, which are very, in most of the cases, which are very justifiable constraints. They are constraints which are either economic constraints. You cannot afford to procure different sizes of the pipes. You cannot afford to procure different sizes of the nozzles, and those becomes your constraints. But in the beginning, when you go in for a fresh design, then you have a choice. You might do a very detailed design, even to look at the conditions, how the crops will vary from one season to another season, whether the same set of equipment will be able, when you will be able to use in those conditions also. So you might do a detailed design for all the combination of conditions which you have under your area where you have the farming activity going on. The sprinkler spacing. The sprinkler spacing is a very important aspect which we have been referring to quite often, that most of the time the sprinkler spacing will be the most influencing factor in terms of whether you are talking in terms of the uniformity coefficient. The sprinkler spacing is the one which can be manipulated. The sprinkler spacing will also be important when you are trying to incorporate the wind conditions. That again, you want to alleviate all the ill effects of the wind conditions through the proper choice of the sprinkler spacing. So when you are talking in terms of sprinkler spacing, you have to first decide what are the wind conditions which you must account for. As if you take the wind conditions of the daytime, invariably the daytime wind conditions will be more severe than the nighttime wind conditions. the wind velocities during the daytime will be much higher than the nighttime wind velocities. That is what has been observed all over the world in most of the places. So the daytime wind conditions are more severe. If you base your design on the data which is only taking account of the daytime wind velocities, then you are going to have estimates which will be conservative estimates. The design will be conservative because you will have higher wind velocities. You will try to account for that by having more overlap. Thereby, you will have an overlap which is excessive, which may not be required. So, the design will be more conservative. It might be over design. Whereas if you take the night wind conditions on the other extreme, and your actual operations are in daytime also, then it can be the other way around. So what you do normally is that when you are going in for the designs, when you go in for the selection of the sprinkler spacing, you try to take the average conditions, or you use a weighting factor which will give some weightage to the night conditions and give some weightage to the day conditions, and you can have a trade-off between the two. So in that situation, at the same time, I think it's also equally important that if the farmer is quite sure that when he is going to use this system, if he is certain that he is going to use only during the night time, then even if you take the night conditions, it will be safe. Otherwise, if you want to change your mind at that time, it will be at the cost of having a very low efficiency, because if the wind conditions are higher than what you have assumed in the designs, is going to give you a design which will be very ineffective, or it will be on the other extreme. It will be a under design situation. So when you are looking at these sprinkler spacing aspects, you will have to take the proper wind conditions. There are, again in this situation, there are recommendations which are available to account for this aspect. With respect to the wind speed, which is given in kilometers per hour, the sprinkler spacing and fraction has been provided as a ratio between SL and DW and SM and DW. The spacing has been provided with respect to different wind speed conditions as a fraction, as a ratio between the spacing and the wetted diameter. When the wind speed conditions are very low, these are the recommended ratios. Now this type of information you can always use to find out what will be the dW under different wind conditions. You can evaluate, if you know that what is the spacing, or if you can choose your spacing, because spacing normally as a function of, again, you have the existing laterals. The spacing will be, when you buy the laterals, you know that what is the spacing of the lateral spacing, or the spacing between the two sprinklers, which is normally available, or which becomes a constraint on the farmer's side, that you have a lateral which is having a fixed spacing. Similarly, when you take a main, you know that what is the point where the main can be tapped, or you can fix the lateral at those locations. So that fixes the main line spacing. SM. In general, you will find that the main line spacing is invariably larger than the lateral spacing. Why that is so? And this is again because of the economic constraints. If you have the main line spacing, if is lower, or if you have more spacing on the main line, all the gadgets which you require whenever you attach the lateral, those can be reduced. So from that angle, is invariably the lateral spacing is kept kept less than the main line spacing. That is a very usual trend which is used in this sprinkler irrigation system. In some cases, you might have the equal spacing also. So looking at some of the usual spacings which are used in the sprinkler irrigation system, you have the spacings which are with respect to the same three categories which we had earlier looked at, depending on the type of crop which is under question. You have, if you have the specialty crop, which is having more value, in that case you might go in for the spacings like 9 by 12 or 12 by 12 or 9 by 15 meter. Now the variations in these spacings are also dependent on how much is what is the wind condition. So you can choose the spacings along with the situation, that what is the wind condition prevailing in those localities. Then for field crops, the spacings which are used are slightly higher than the previous case. And when you have the orchards, the spacings can still be wider, because in that case it will be a function of what are the spacings of those individual trees or those plants. in conjunction with the spacing, there is one aspect which is very important, which is the aspect of offsets. This is a very recent phenomena, and it pertains to the operation of these sprinkler irrigation systems. That if you can use the offsets, first of all, let's try to see that what do you mean by the offset. Let's assume that you have a main line, and out of this main line you are taking off, I am not connecting it deliberately, you are taking off the laterals on which you have the sprinkler heads, and they are with respect to the spacing between the laterals, they are spaced accordingly. This is the total the 4 sets of laterals. So normally you attach them here onto the main line. In this case, the spacings which are relevant are, this is the spacing between the laterals, or the lateral spacing and the main line spacing. Okay. Now we have seen that when we want to operate the system in this manner, we have to look into the overlap. The design contains what should be the SM, what should be the SL, so that we can get a appropriate overlap, so as to reduce the depercolation losses and to increase the efficiency, the uniformity. But we have seen that invariably, if we look at the total field, a part of the field will be over irrigated, a part of the field will be under irrigated, depending on how much is the total depth of water you have applied. So if you want to keep a balance, if you want to keep the losses minimum, you might do so by sacrificing the requirement that all the field should be getting the minimum required, or the net depth. In some portion of the field, you will deliberately keep the depth lower than the net depth required, so as to reduce the depercolation losses to the minimum possible level. Now, if you can, let me put it like this. Let's try to have a look which we had plotted earlier. We had depicted that through a plot, that if this is our field and this is our net depth of application which is required, if we have 50% adequacy, with respect to 50% adequacy, you might get a situation where you have in this situation for a specific level of the uniformity coefficient. If I want to reduce this this deficit as well as this percolational loss. This I am getting mainly because of the fact that the overlaps are not very accurate. They don't give me a uniformity coefficient which will ensure that all the places I am getting the equal depth. And that this situation can be improved drastically if I change the spacing, if I can have a control on the spacing in such a manner that I use one spacing at a particular time. The spacing remains same, but the location of the lateral in the next irrigation I can change. For example, if I have in one irrigation I have this setup, and the next irrigation, instead of using the lateral at this location, if I can use the lateral at this new location, which is in between the two existing locations, then this will be the place where I can place my lateral, and the next lateral I can place at this location. The next lateral similarly I can place at this location. If I get this flexibility, then I might be in a position to apply the depth, which is the replica of this. It means those portions where there was a deficit earlier, they will get additional water, and those portions where there was additional water earlier, they will be getting deficit now. So if that happens, then what I have done is that I have superimposed another application which is just opposite to this. Or if I put it from upside down, I might get another application which is like this now. We are just matching with this. It might not match exactly like this. So over two applications, over two successive applications, I will get this total depth, out of which wherever there was a deficit earlier, here I had the surplus earlier, but now I have a deficit because now I am this is my level of, I have put it upside down, so I have a deficit in this area. As still for the next also there is the same level, which is the required level of application. So by using this is what is known as the offset, that I have offsetted the position of the lateral in between the previous position of the two laterals, and that you can easily do by having a hose. You might have a connection through a flexible hose, so that the water can easily come into this, and then the next case this connection remains same, but you can physically locate it there. So this type of system, this type of offset is very easily possible with the side roll system, where you have the whole thing mounted on the wheels. You have to move it, is only the position of the placing of the lateral which has to be changed. It has been found that this type of offset, the use of offset, in this particular case the spacing can be SM by 2 or any other spacing, because now you have the total flexibility. Looking at what overlap you want, you have complete flexibility, and by doing so, it has been seen that is around, it can give you an advantage up to around 15% additional uniformity coefficient. Though it will vary from what is the existing uniformity coefficient and how much it can be improved. If it was very poor, it can be improved more. If it was a good uniformity coefficient earlier also, that means in any case your overlaps were quite reasonably good. Yes.
So is this equivalent to reducing the spacing by factor of 2? Mainline spacing.
No, it's not. You are not reducing the spacing. The spacing is still the same.
Yeah, of course.
The spacing between the two remains the same.
But virtually you are applying twice now, sir. Once you are applying with the same spacing, and after that you are repeating the same spacing in between the rows.
Now I think there is a slight, and I have to make another additional statement which I have made but which I have not caught. This is not to be done over the same irrigation. These things are to be done over the successive irrigations. In one irrigation you are using this setting. When you go to the next irrigation, then you are using the change setting. So then is not what you are saying. I mean, you have to look at, maybe the efficiencies have to be worked out in terms of the total period of the crop growth. But even if you will look at the efficiencies of two successive irrigations, that is how you have to work out. Otherwise, the efficiency will remain same. But what we are interested in is the efficiency in terms of the overall, because in the previous case, when we were keeping everything fixed, all along throughout the total period of the crop, those areas which were getting less water, they are getting less water. And those areas which are getting more water, they keep on getting more water throughout. So that is avoided here, and that makes a lot of difference. Because if you have put in more water, that means you have brought it to the field capacity level at least. As it won't retain anything beyond that. All the deep percolation loss has gone out of the system or beyond the root zone depth. The only additional advantage is that the deficit is now distributed. Okay. Yes, please.
Can we do the same thing with the nozzle location if we shift just by half nozzle location? I mean, we move this lateral SL by 2 in the new location.
In which direction?
In the same direction in which direction the laterals are placed. If we shift the lateral by SL by 2 distance, then the nozzle will be in the new position, and the distribution which we are getting in this diagram will get just the perpendicular shift.
Yeah, that what he is trying to say is that if we do the same thing with the lateral also, and the lateral you want to shift in this direction, that is also possible, because once you are is the overlap which you are having, and the overlap is not from one side, is from both the sides. So you can resort to that also, which is again possible by having a longer hose pipe. You can even do that. So that combination can also be tried, but then it has to be there has to be some systematic way of doing it, and that I fully agree that that will also have the similar impact, if not the same impact. Because why this is being done is, as in most of the cases, as we have just said, that the SM is much larger than the SL. So the advantage which you are getting is more if we manipulate the SM than the SL. What you are recommending is that we should manipulate SL, but SL as such is less than SM. So the overlap might not change very much even if you do that. Okay.
So it is more convenient to change this.
It is more convenient to change this than to change in this direction, because this direction you have already gone to the end of the field. Your length of the lateral is basically matching the length of the field invariably. We'll come to that when we'll come to the layout of these systems. Okay. Any other question? Thank you. Then we'll stop here.